Okay, so we went through the first couple figures in chapter 1. We're gonna pick it up next week, finish chapter 1, go ahead and read that on your own, but basically what I'm gonna do, going through the chapters, is just flip through the figures, because they really summarize the big picture in each chapter, and that's what I wanna, mainly focus on in lecture, to make sure that we're kind of getting that big picture stuff. Before I let you go today, though, I'd like to just start looking at summary 1. I haven't talked much about this biosketch, but if you could, I would like to learn a little bit more background on each of you in terms of how you came to be interested in renewable energy, and then kind of where you hope to go with it. I've had that opportunity a few times. I've given talks, and it's always kind of fun to do some self-reflection. So if you could do that for me by next week, and it's nothing big, just kind of sit down, write, 500 words would be fine, but just something to kind of
Just
get.
500 words about myself, okay.
Is that going to be in the forum that we discussed, or as a?
I hadn't thought about that much.
I think it would be interesting. I don't know if people want to share,
Yeah, I like the suggestions. Let's put it in the forum. I mean, just kind of got nothing to hide here. So yeah, 500 words, and let's just do that kind of between now and Tuesday, and then we'll look at it a week from today, and I know I'll find it valuable. I do it all the time. But then let's look at summary 1, so you can at least get reading on that as well. Exam 1 is not until week 4, so we've got plenty of time to get through the first 3 chapters, kind of a chapter a week, and we got through a portion, almost half of chapter 1 today. But let's take a look at that first summary. Problem set 1. Okay. And then we'll get into the problem sets as well, but I wanted to first start looking at this summary. Okay. So since NRGY 102 is cross-listed with climate change 102, I thought this was an appropriate topic. It's a little more science-y than some of the other things we do, which are a little more techy. But what this group has done with this paper is sort of made an imaginary fantasy world where all fossil fuel consumption ends in the year 2050. So there are some climate talks, China and U.S. negotiations saying, okay, if we're going to do this, we got to do it for real. We're going to phase out fossil fuel, carbon-based fuels at some point, either by design or by default. We're either going to say we're going to get off the carbon fuel bandwagon by policy and as expeditiously as possible, or we're going to burn them all up. I was just in this coal mine in eastern Montana, and it was a trip seeing the coal just disappearing from the ground, and then the machine goes and covers up where it was, and it's gone. I mean, it's not coming back. So, this will happen either if we make it so, or anyway, burn it all up. I don't know. But what the authors are trying to show here is that nature has a finite capacity to resorb CO2. And this is just based upon what nature is capable of doing. The trees, the grasses, the plants, the algae in the ocean, they have a metabolic rate, right? They can only process CO2 at some rate. What they're trying to show here is that even if all carbon emissions cease, if just kind of nature has its way, it's still going to be kicking around there for a long time until somebody comes up with artificial tree, artificial carbon, some other way of taking this stuff out of the atmosphere, making oxygen, putting carbon in the ground. Chances are there's going to be some kind of engineering solution to it, but this is kind of, nature doing its thing. The other take home here is that other gases, like nitric oxide, have a shorter half-life in the atmosphere than CO2 does. It's also showing that methane has an even shorter half-life as well. It's a more powerful greenhouse gas in that the band gap at which methane absorbs the energy from the earth that's radiated back into space hangs on to that energy more tightly than CO2 or N2O, and thus this type of curve. But that's really the big picture on this paper. And here's the key equation, and I think Tim showed this equation in class on Tuesday. What I'd like you to do is look at this thing and tell me whether it's an energy equation or a power equation, right? Because when we were doing our human metabolism, we were mainly dealing in power. We took energy divided by time and turned that into a power equation. I want you to tell me whether this is an energy equation or a power equation and what the units are. It looks like it's energy, because it says right there where F is the added energy. But if it's energy per year, then it's a power equation. Okay, so and it could be that it's so just think about that. It's important and it's fundamental. Also, look at this thing, because I think the second we do, I think you might change your mind as to whether this, because at first glance it looks like an energy equation. This thing, though, if I take N, which it's either energy or power, and right here I'm multiplying it by time. The D just means a change, and T is obviously time. It looks a heck of a lot more like N is actually power, because if I multiply power by time, I get energy. So these guys are, I think, probably pretty good scientists, but it looks like the way they wrote it is a little confusing. Nothing's perfect. But I'm pretty sure this is a power equation. This is obviously temperature, and we're going to get into this a little bit later in the semester when we look at my paper, because the units on this thing, this lambda, are a little wonky, but we will be able to define exactly what lambda is shortly, based on some of the dimensional analysis that we've done. So that's your key equation for this paper. I want you to put an equation in your own summary, like we talked about, cite it, and it's going to look a lot like this. Hopefully you'll do a little bit better and make it clear what the actual dimensions are on the variables. And then I'm also going to ask you to go in and find another citation. I kind of like this one. The paper I keep looking for, and if somebody in this class could find it, I would love it. The paper I keep looking for is the experiment where somebody just took a bottle full of CO2, a bottle full of methane, and a bottle full of air, and just left them out in the open for a while and looked at their changes in temperature over time. I'm thinking that the CO2 and the methane are just going to automatically get hotter. I mean, they're greenhouse gases, and they're going to absorb more of that energy. I haven't seen that paper yet, and I kind of want to do the experiment. I just want to go over to chem stores, buy some CO2, get some carboys, fill them up, and then just fire our thermal cameras at them and see what we get. But anyway, because most of this, what we see in this paper, is based on global modeling. But I would love to just see the benchtop experiment where they kind of did this experiment. Okay, well, thank you for your attention, and we'll see you on Tuesday. And I look forward to those bio sketches. I'll do mine too.